everyone, my name is Aisha Williams, and today I will be doing my presentation on significant figures, which are also known as Sig Figs. Now, there are three main rules that you first have to start out with before you can even get to the operations using Sig Figs. The first rule has to do with leading zeros. Now, an example of leading zeros would be a number such as 0.000485. The leading zeros in this number would be all of these zeros right here. Now, these zeros are never significant. Never significant. An easy way to tell when you're having to deal with leading zeros about whether the number is significant or not is to actually put the number into scientific notation. So for example, this number that we have right here, 0.000485, in scientific notation, this number would be 4.85 times 10 to the negative fourth power. Now, as you can see, this number right here has three significant figures. These three numbers, because they're non-zero numbers. So this number right here has three significant digits. The next rule that you will be using during Sig Figs has to do with trailing zeros. Trailing zeros. Now, trailing zeros are a little bit more complicated because there are two rules associated with trailing zeros. The first rule has to do with numbers that have zeros after the decimal point. So an example of that would be a number such as 4.0. Now, this number right here has two significant digits because the zero comes after the decimal point, which makes it significant. An example of where this is not true would be a number such as 4,000. Oh, I'm sorry. Let me write this. Significant. Now, this number right here, 4,000, is what we would call an ambiguous case. This means that the number of significant digits in this number cannot be determined because it ends in zeros. Now, a number such as 4,000 with a decimal point behind it has four significant figures. As we did up in here, if we wanted to write this number right here in scientific notation, that would be 4.000 times 10 to the third power. So here we have trailing zeros. We have three different cases. The first one, 4.0, the zero comes behind the decimal point and therefore is significant. In this number, the zeros come after the number and there are no decimal points within the number, which makes it an ambiguous case, meaning that we cannot determine accurately the number of Sig Figs in this number. This number, 4,000, has a decimal point right here. Let me make sure you can see it. Right here, behind the number, and therefore it has four significant figures. And this is 4,000, the same number right here, written in scientific notation. The last case of the zeros, as I like to call them, is called with embedded zeros. Excuse my handwriting, I'm a little bit left-handed. Yeah. Now, embedded zeros are zeros that are written between two non-zero numbers. So an example of an embedded zero would be a number such as 403 or 5002 or something like this. And so in both these cases, the zeros are significant because they're between two non-zero numbers. So this number right here has 3 significant digits, and this number right here has 4 significant digits. 4 Sig Figs. And these is the basis of the rules for significant digits before you get into operations, because you have to understand how the zeros work in order to accurately do the operations, such as multiplying, dividing, adding, and subtracting, which we will be getting to next. Now, the 4 operations that we do with significant figures have 2 rules total. The first rule goes for addition and subtraction. And the second rule goes for multiplying and dividing. Okay, you write one so we can keep us organized. Okay, now, when adding or subtracting, the answer contains the smallest number of decimal places of the addends. So, for example, if we have 23.07 plus 42.1, without rounding or doing any other calculations, just adding, we get that answer 71.56. So 65.17. Now, this number goes out to the hundredths place right here, and this number goes out to the tenth place right here. So our answer can only go out to the tenth place. Therefore, we end up with an answer with significant figures of 65.2. This number goes out to the hundredths place. This number goes out to the tenth place. So our answer can only go out to the tenth place, which is marked by this 2 right here. Another example that we can do is one with subtraction. So for example, if we have 52.874 minus 30.25, we will get an answer of that's 22.624. Yes, 22.624. And that is without doing our significant figures yet. Now, this answer goes out to the thousandth place. And this answer goes out to the hundredths place. Therefore, our answer can only go out to the hundredths place. And we end up with an answer of 22.62. This number goes out to the thousandth place. This number goes out to the hundredths place. Therefore, our answer can only go out to the hundredths place, as marked here. Now, something that confuses some people is when you have a number such as 83.425 plus, let's say, 45.624. Let's just go with that. When you add these 2 numbers together, you will get 9. 4, 0. Now, this number has 5 significant digits and goes out to the thousands place. This number has 5 significant figures and goes out to the thousands place. However, this number has 6 significant figures and goes out to the thousands place. Some people may ask, well, how can you have 5 Sig Figs here and here, but have 6 Sig Figs here? Now, this is completely acceptable because with addition and subtraction, your answer contains the smallest number of decimal places of the addends. And the smallest number of decimal places in both cases here is the thousands place. Therefore, our answer should go out to the thousands place. With addition and subtraction, the actual number of Sig Figs that you have in each number is not the case. You go by the smallest number of decimal places, which in this case happens to be the thousands place. Now, the last case that we will be going over today is the case that has to do with multiplying and dividing. When you're multiplying and dividing with Sig Figs, the answer has the smallest number of Sig Figs of the factors. So, for example, if we have the number 2.0083 times 2, this number here has 1, 2, 3, 4, 5 Sig Figs. The zeros in this case are significant because they're between two non-zero numbers. This number here has 1 Sig Fig. It does not have a 0 behind it, which would not make it ambiguous, but it does have 1 Sig Fig. So 1 Sig Fig. Now, when we multiply this number out, we get a 6. 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Now, with multiplication and division, the rule states that the answer has the smallest number of Sig Figs of the factors. This number has 5 Sig Figs, as we previously discussed, and this number has 1 Sig Fig. Therefore, our answer can only have 1 Sig Fig. And when we round it and we use significant figures, we get an answer of simply 4, which, like 2, has 1 significant figure. A problem using division could be, to make it easy on everybody, 121 divided by 11, which we would say is 11. This number has 3 significant figures, and this number has 2 significant figures. Therefore, this number can only have 2 significant figures. And it just so happened that this worked out the right way. But if we have something a little bit more complicated, such as 202 divided by 2, and where we get 101 is the answer. This number has 3 Sig Figs, so 3 Sig Figs. Let me make sure. This number has 1 significant figure, so that's 1 Sig Fig. Therefore, our answer can only have 1 significant figure, as the answer has the smallest number of Sig Figs of the factors, which are here. Therefore, this would end up being 1 times 10 to the second power, which is equal to 100. But we're rounding, so you get 1.0 times 10 to the second power. 3 Sig Figs, 1 Sig Fig. Our answer can only have 1 Sig Fig, as is demonstrated right here. Now, thank you for listening to my presentation, and I hope you learned something about Sig Figs.